Welcome to month 2 of the DevOps engineer track. Last month, you built a CI pipeline. Today, you're going to fix what it's building. 3 services that run as root in one, 2 GB images with floating latest tags. By the end of this session, every image will be multi-stage, non-root, signed, and passing a Trivy vulnerability gate. This month is about supply chain security. Containers are the packaging boundary between your code and production. If the package is insecure, everything downstream is at risk. Let's be concrete about what's wrong with BISTEC Mart's current containers. 3 issues, all fixable today. Issue 1. 2 GB images. Single-stage Docker files pull the entire Python dev toolchain into the production image. Pip, compilers, test runners, none of that belongs in production. It bloats CI, slows deploys, and expands the attack surface. Issue 2. Running as root. When every service runs as root, a container escape gives an attacker immediate host privileges. The security team flagged this as a critical finding. It's a one-line fix, but only if your Docker file is structured to support it. Issue 3. Floating latest tags. Latest is non-reproducible. It means the most recent build at the time someone last pushed, which can be a different image on every machine in your fleet. You cannot roll back to latest reliably because it moves. What we're fixing today: multi-stage builds to shrink images, non-root users with explicit UIDs, and pinned git.sha tags. These 3 changes close the current audit findings. Every Docker image is a stack of immutable layers. When you write from Python 3.12 Slim, you're starting from a set of pre-built layers. Each run, copy, and add instruction adds a new layer on top. The Union file system merges these layers into a single view at runtime. Layers are immutable and content addressed. If 2 images share the same base, they share the same layer bytes on disk and in the registry. Harden deduplicates these automatically. Layer order matters because Docker's build cache works top to bottom. When any instruction changes, the cache is invalidated for that layer and every layer below it. If you put copy/app early in the Docker file, every time any source file changes, every subsequent layer, including the expensive pip install, runs from scratch. The rule is, put rarely changing instructions first. Base image, then system packages, then application dependencies, then source code. Your source code changes on every commit. Your dependencies change far less often. When you run Docker build on a directory, everything in that directory is tarred up and sent to the Docker daemon before a single instruction executes. This is called the build context. If the directory contains a node modules folder with 200 megabytes of JavaScript, that 200 megabytes is uploaded on every build, even on warm cache runs. The Docker ignore file works exactly like git ignore. Patterns in it are excluded from the build context. Ignoring git node modules, venv test directories, and documentation shaves seconds off every build and prevents accidental inclusion of sensitive files. The sensitive file case is the dangerous one. If env is in your build context and your Docker file has a copy with a wildcard, that file lands in a layer. Docker history can expose the contents. The Docker ignore is your last line of defense against leaking secrets into images. Choosing a base image is a trade-off between size, security surface, debuggability, and compatibility. Scratch is an empty base. 0 bytes, no shell, no libc. It only works for statically compiled binaries, Go or Rust services that link nothing at runtime. The attack surface is minimal, but there's no shell to exec into when something goes wrong. Distroless images from Google are around 20 megabytes, no shell, no package manager. They include only the language runtime, perfect for production. You can use Docker debug in Docker Desktop when you need to inspect a running container. Alpine is 5 megabytes and includes a shell. It uses muscle libc instead of glibc, which can cause subtle DNS resolution bugs that only surface under load. Debian Slim is the balance point for most teams. 80 megabytes, glibc, apt, enough tooling for CI debugging. Full images are for local development only. Never ship a full Ubuntu or Debian image to production. For BISTEC Mart, Python 3, 12 Slim as the runtime base for catalog and worker, and Engine X1, 26 Alpine for the storefront's Engine X stage. The build stages can use heavier images. They're discarded in the final image. The multi-stage pattern is the single biggest impact change you can make to your Docker files today. Use one stage to build your application and a completely separate, smaller stage to run it. In the catalog Docker file, the builder stage starts from Python 3, 12 Slim and installs all Python dependencies into /root/local. That stage does nothing else. The runtime stage then starts from a fresh Python 3, 12 Slim and copies only the installed packages from the builder, not the build tools, not the cache, nothing else. 3 things to notice. First, both stages use the same base image to avoid lib version mismatches. Second, the copy from =builder instruction uses the chown flag, so files are owned by the non-root user from the moment they land. Third, user 10001, a numeric UID, not a username. This works even in distroless images where there's no /etc/password file. The result, catalog goes from 2 gigabytes to 187 megabytes. Storefront with a node build stage plus Engine X runtime goes from 900 megabytes to 64 megabytes. That's not a tuning improvement, that's a category change. BuildKit is the build engine behind Docker Builds. It unlocks 2 features that improve build speed and security. Cache mounts let you share a directory between builds without committing it to a layer. The mount type = cache syntax tells BuildKit to persist the pip download cache across builds. On a warm build, pip finds its packages already downloaded and skips the network. The cache directory never appears in the image. It's build time only. The same pattern works for npm, yarn, and apt caches. Secret mounts solve a different problem. Credentials that must be available during a run instruction, but must never appear in the final image or its history. Setting an env variable or an arg for a secret ends up in Docker history. Secret mounts provide the credential as a temporary in-memory file that exists only for the duration of that one run instruction and is not stored in any layer. Secret mounts require Docker build with the secret flag at build time. A tag like Python 3, 12 Slim is mutable. The image registry team can push a new image with that tag at any time. Your Monday build and your Friday build may use different underlying images even if your Docker file is identical. A digest, the SHA-256 hash, is immutable. It refers to exactly one manifest forever. If you reference Python 3, 12 Slim as specific SHA-256, you're pinning to an image that cannot change. Your builds are now reproducible across time, across machines, and across CI runners. To get the digest for a tag, run Docker BuildKit image tools inspect with the tag and a format flag to extract the manifest digest. Add that to your from line. Update it consciously on a schedule after reviewing what changed. The multi-architecture story. BuildKit can build for Linux/AMD64 and Linux/ARM64 in a single push. Harbor stores an OCI image index that maps each platform to its architecture-specific manifest. A developer on an ARM MacBook and a CI runner on an AMD64 server both pull the same tag, and each get the correct architecture automatically. Docker Compose is a declarative specification for multi-container applications. Everything you need to run a service, image, environment, ports, networks, volumes, secrets, health checks, startup order, is expressed in a single YAML file. The 4 top-level keys matter. Services defines what runs. Networks defines isolated communication channels. Volumes defines persistent or shared storage. Secrets defines secure credential injection. Health checks are the feature most teams skip until something breaks in production. A health check tells Compose whether a container is actually ready to serve traffic, not just running but healthy. You define a test command, an interval, and a retry count. Other services that depend on it with condition. Service healthy wait until that condition is met. This is the difference between the container is running and the application inside is accepting connections. Composed networks are an easy, cheap way to enforce service isolation. By default, every service in a composed file can reach every other service. That's fine for development but wrong for a security-conscious environment. The BISTEC Mart stack has two networks, front-end and back-end. Storefront is attached only to front-end. It can accept traffic from outside, but it cannot make direct connections to the database or RIDIs. Catalog bridges both networks because it needs to accept API calls from Storefront on front-end and connect to Postgres and RIDIs on back-end. Worker is back-end only. When a service is not attached to a network, it cannot reach services on that network at all. DNS resolution fails. This is not a firewall rule you have to maintain. It's enforced by the composed network model itself. To verify, try pinging Postgres from the Storefront container. It will fail. That's correct behavior. Harbor is an open-source container registry with built-in Trivy scanning, role-based access control, content trust, and image replication. It's a self-hosted alternative to Docker Hub. 3 steps to start using it. First, trust the CA. Harbor in the lab uses a self-signed certificate. Your Docker daemon won't pull from it until you install the CA certificate and restart the daemon. This is a one-time setup per machine. Second, log in with Docker login and the registry address. For SI, use a robot account with write-only push permissions, never your admin password in a pipeline. Third, push with a git SHA tag. The convention is the registry address, / the organization, / the service name, : the short git SHA. The git SHA gives you exact traceability. Every image in Harbor maps to a specific commit in your repository. On branches other than main, tag only with the SHA. On main, also push a latest tag for convenience, but the SHA tag is the one that goes into deployment manifests. Trivy is an open-source scanner from Aqua Security that scans container images for vulnerabilities. The key flag is exit code 1 with severity high, critical. This makes Trivy fail your build when it finds unfixed high or critical vulnerabilities. Add ignore unfixed to skip findings where there's no fix available yet. Those aren't actionable, and noisy reports get ignored. When you must suppress a finding, for example, a high-severity CVE in a library you can't upgrade without breaking your application, use a Trivy ignore file. Every entry in that file must have a comment with a date and a reason. Suppressions without dates rot. 6 months later, no one knows if the CVE is still relevant or if the library was updated. An SBOM software bill of materials is a complete inventory of every package inside an image. Trivy generates them in SPDX-JSON format. After you push an image to Harbor, attach the SBOM using Cosign. This lets anyone who pulls the image verify what's inside without running the scanner themselves. Cosign is a tool for signing and verifying container images. Signing answers one question. Did the image you're about to deploy come from the CI pipeline you trust, and has it not been tampered with since? There are 2 modes. Keyless signing uses OIG, the same identity provider your CI system uses. When you run Cosign inside a GitHub Actions workflow, it gets a short-lived certificate from SigStore's Fulcio Certificate Authority that proves the signing happened in a specific workflow at a specific repository. No key management. No secrets to rotate. The verification command checks the certificate identity against the workflow URL. Local key signing uses a key pair you generate. You sign with the private key and verify with the public key. Simpler to understand, but you're responsible for protecting the private key. For production CI, keyless is usually preferable because there's no key to leak. Either way, you sign the digest, the SHA-256 hash, not the tag. Tags are mutable. Signing a digest means the signature covers exactly the bytes that were pushed. Containers fail. Knowing how to diagnose failures quickly is a core DevOps skill. Docker exec drops you into a running container with an interactive shell. On a distroless image, there's no shell. Use Docker Debug in Docker Desktop, which injects a minimal debug toolbox, or add a debug stage to your multi-stage Docker file that you never ship. Logs. Docker logs with the tail and follow flag streams recent output. Containers should write to stdout and stdir, nothing else. Know where the JSON log files are on disk when you need to grep them directly. Docker inspect returns every detail about a container's configuration as JSON. The most useful fields: state, which tells you if it's running and what the exit code was; config; env, which shows what environment variables were injected; and mounts, which shows what volumes are attached. Pipe through JQ to extract specific fields. Docker Compose PS shows the health status of every service in the stack. A service stuck in starting is failing its health check. A service in exiting is crash looping. Both tell you exactly where to look. Here's the challenge. You have the same 3-service BISTEC Mart stack from month 1, but the Docker files are single stage, running as root with latest tags and no health checks. Your job is to fix all of that. 4 deliverables, 25 points each. Deliverable 1. 3 Docker files, multi-stage, non-root user with explicit UID base image pinned by digest. A health check instruction, lint clean. Deliverable 2. A compose stack with all 5 services, correct network segmentation, health check gated dependencies, and compose secrets for credentials. Deliverable 3. A publish script that builds with builds, runs a Trivy gate, signs with Cosign, and attaches an SBOM. Deliverable 4. A hardening report that shows before and after Trivy findings, documents every suppression, and explains every hardening decision. 2 non-negotiables. 0 unaddressed high or critical Trivy findings before anything leaves CI, and every published tag signed with Cosign. Your offline milestones extend the challenge in 3 directions. Switch the catalog runtime base from Python 3.12 Slim to a distroless image and measure the size delta. Add image signing verification to the month 1 CI pipeline and make unsigned images fail the build. This closes the supply chain loop. Add a size budget CI step that fails the build if any image exceeds its target size, preventing image bloat from creeping back in over time. For reading, the Docker docs on BuildKit and multi-platform are the canonical reference. The compose spec at compose spec. EO is the formal schema, useful when you're debugging whether a YAML key is valid or deprecated. Liz Rice's Container Security covers everything we touched today and goes deeper into Linux capabilities and seccomp profiles. Take a moment to reflect on what changed today. You started with 3 services that were a security audit's worst nightmare. Root user, 1. 2 GB images, floating tags. You're ending with signed, scanned, pinned images in a private registry, with a compose stack that enforces network boundaries and health check gated startup. The principles you applied today: least privilege, immutability, explicit dependencies, supply chain verification. These aren't Docker specific. They transfer directly to Kubernetes, where pods run with security contexts. Images pull from the same harbor registry, and you define the same network policies at the cluster level. Month 3 is Kubernetes fundamentals: pods, deployments, services, config maps, secrets, ingress, horizontal pod autoscaler, and a working Git ops deploy pipeline with Argo CD. Everything you built today is the foundation for what runs in Kubernetes. See you next month.